I'd like to thank Yann Klinger, Robin Lacassin, Martin Simoes, and all those who helped organize this wonderful workshop to celebrate the extraordinary legacy of Paul Tapponnier. I think he would be proud of the science that has been presented in his name. And yes. So in this talk, I will start with a few slides about my journey working with Paul. And then I will present some results from recent research we've done in my group. And that won't be about the India-Asia collision zone. It will be about earthquake in my backyard, earthquakes in California. So we've heard that the great man was deeply in love with sports. And that's really true, and that was no secret, actually. Not long after I graduated, he was featured in a full pages article of Télérama, which is a well-read magazine in France. And the article was about his passion for science, sports in particular. And I think the journalist did quite well at capturing his personality. I translate what is said here. In a plane, in a jeep, or in hiking boots, Patogas is a well-known brand of hiking boots. It tracks the faintest fault, the faintest jolt of our planet, Mr. India-Asia collision. Yeah, so that was really him. So my journey with Paul started when I was looking for an internship. I was still in my engineering school. And then I realized that working with Paul, you could go to Tibet. And yeah, that's what I want to do. And so I met with him, and he offered me an internship. And I got my first fault. That's my first fault. I studied. And so that fault is nice, right? Well, he didn't take me to Tibet because actually he spent all the summer in Tibet. I was studying this fault in the basement of IPGP, where I was doing some analog experiments using an apparatus that Gilles Perzer had designed just before leaving for the US for his postdoc. So he designed the apparatus and then he sent me to the basement to play with it. So but I learned a lot from that. So a few years later, he finally took me to Tibet. And that's been a really great experience to learn with him field geology, starting with sketching in a notebook. I didn't know anything about geology when I started my PhD, so I had a lot to learn. And as you can tell, I was trying hard to look like my master. When I saw this picture, I could not believe it now. I need to grow a beard, I guess. So at the time, Paul was actually the first using spot images to study active faults. And so during my PhD, I followed the track of what Gilles had done, Paul Armijo before, looking at the geomorphology of set-by faults and then try to inversely prate on faults. So it was great at reading the landscape in the field, but also using satellite images, and we've heard that many times during the workshop. It was great also at seeing the big picture, so at connecting observation you can make in the field and satellite images and then figure out what's going on at the large scale. And it was great also at getting into controversies, and that's something I learned from him. You don't shy away from controversies. If there's a controversy, it means that it's an interesting topic. There's substance there, and you stand your ground as much as you can. So yeah, that was the controversy about the degree of localization of continental deformation. There was two teams at the time. So those who were seeing continental deformation more like a fluid-like behavior, and then the faults would just be a very superficial manifestation of distributed deformation at depth. And in models, we should not care about faults. We should care about what's going on at depth. So we treated that like a fluid. And then there was more like faults team, thinking that maybe faults were actually a big player in driving the deformation at the large scale. So yeah, that was the work we've done at the time. So I would say, I would not say that we were necessarily 100% right. I mean, the slip rate we had on the fault were a bit generous, I must say, but the mission of India was also a bit generous to get started, because at the time, Avouac was giving us something like 5 centimeters per year of convergence. So we could make it work with relatively large slip rate on the Altintac fault and so on. Now that it's down to about 4 centimeters per year, since it has been revised, actually it's easier to deal with smaller slip rate, but the end result is the same. Most of the strain is localized on a very few large faults bounding a small number of faults. And actually, if you look at the velocities relative to regia that are predicted using a simple block model, there are only 5 blocks in that model, and you compare with GPS, so this is the same velocity field plotted differently, but with the same projection as what you see here. With GPS, it's very close, actually. So, yeah. So we were about right. So that's what I learned. I mean, I learned a lot more for Paul, but I wanted to start from that. So after my PhD, when I had been using spot images to interpret the landscape, more in a static way, I got interested in trying to use such images to actually measure increment of deformation by comparing images before and after an earthquake. And so I got the good luck of having excellent students who helped me with that. So that started with Rémi Michel, who was actually a student in my group at the same time as Jan Klinger. And so the game was to actually correct all the geometric artifacts in those images so that you would get enough accuracy that after you could correct them and measure deformation. So it's not been easy to get this to work, but it has matured quite quickly thanks to the help of all of that. And here is just an example of results from this technique. So this is correlation of images acquired before and after the Kashmir earthquake of 2005. And you see clearly the fault trace from the discontinuity in the displacement field, right? And you can actually measure from these images the slip vector, actually the horizontal component of the slip vector, which is shown by these arrows. So here, what is advantageous is that you don't need to have features like a road being offset by a fault. You can measure that continuously. And also, it's integrated. If deformation is distributed, you can measure the cumulated deformation across the shear zone. So it's a somewhat different information you get that one you can get in the field, where you would map only those ruptures that are well expressed in the morphology. So let's discuss now with what we can do with such measurements to learn something about fault mechanics and earthquake physics. So here I'm showing measurement made by Saif Hati with the latest student who worked on that technique, and now we can measure the displacement in 3D by using images with different view angles. And here you have only the two components, north-south and east-west component of ground displacement produced by the Ridgeway earthquake sequence. From 2019. So this is the San Andreas fault, all recognized. This is LA, so I'll leave here. And this is where the earthquake happened. Let's see what we measured from this correlation result. So you can run profile across the fault and get the displacement across the fault at regular points. By the way, you see two faults here dominantly. So this is the foreshock, a 6.4 earthquake, which occurred the day before the main shock, 7.1. So the 7.1 was actually this this rupture. So the two ruptures are showing on that slide. So we complemented the measurements from correlation of satellite images with measurement in the field. So many teams were in the field to map so that we could make comparisons. I will say a word about what you learned from that comparison. The first thing I'd like to emphasize here, which shows nicely, I think, on this figure, is that if you look at the amplitude of slip, so the color coding is showing how much slip occurred at each point along the fault, you see that there's a gradual variation. You have more slip here, actually, in that case, near the epicenter of the earthquake. And when you go to the south, you see that you get less and less slip. At the same time, the orientation of the fault is changing. So it looks like there is a correlation between the fault geometry and the amount of slip. There's a little bit of that, too, for the foreshock. It's a little less obvious. But here, it is very clear. And I have been looking for opportunities to see that in previous earthquakes. But most of the time, the ruptures are too complicated to see a nice correlation, such as what we see here. So first, what do we learn from comparing the displacement measure from the satellite images? So the blue points here are showing those measurements along the fault, and the black points are showing the measurements made in the field. Okay, when you look at a road offset by a clear fracture. So first, what you see is that the blue is not the average of the black. If the medium was purely elastic, and you had this, and this would be displacement in an elastic medium, the blue would go through the mean of these black points, and it's more like the envelope. So it tells you actually that you have distributed deformation, you have some inelastic deformation, and you can measure how much inelastic deformation you have from taking the difference between the blue points, which is the envelope of the field measurements, and on the field measurements. And when you do that for the main shock, we get that about 25% of the total displacement across the fault was taken up by distributed shear in a zone that is typically of the order of a few hundred meters width up to a few kilometers. For the foreshock, it's more like 60% of the deformation that is actually inelastic, undistributed. In any case, it is inelastic, but it is distributed. So we call that off-fault damage. So now the next thing you can do, you have the fault geometry, you have the total displacement. That tells you information about the amount of slip at the edge of the fault, right? Then you use geodesy and like I write GPS measurements, you use seismology, and you can derive a model of the kinematics of the rupture, the kind of model that Chenji is mastering. So here, this is the slip rate on the fault as a function of time. So derived from the inversion of high-rate GPS. Here you have the records. And using also the information from surface deformation, the cumulated slip from the optical images. So it's a very nice rupture. It starts, I don't have the map anymore, but it starts where the fault was more toward the northeast, northwest. And you see a nice crack, so evolving into a slip pulse, okay? Which now you have a slip pulse. You see an effect of the saturation of the seismogenic depth, which favor this transition from a crack rupture to a pulse rupture.
That is the 6.4 or the 7.1?
That's the 7.1. Yeah, we don't have such a nice movie for the 6.4, so I'm not showing it. And here you see the bend in the fault that I was pointing to earlier. So one thing you can do is invert for the stress field using focal mechanisms of earthquake before the earthquake or after the earthquake. And here is the work that Chris Miller did. It is very well constrained, right? Sigma 1 is nearly north-south, sigma 3 is nearly east-west. And yeah, so all is clear and simple here. What you can do is compare the stress regime, the stress field before and after the earthquake, and then look at the rotation. And from that, because we have a good slip model, we can calculate the stress change at the location of the aftershocks. And so we can actually compare the rotation of the stress field we can actually derive from the rotation of the stress field the amplitude of the stress tensor, which is very, very difficult quantity. Okay, let me say that again. I guess I'm getting a little tired. From the inversion of the focal mechanism, you get the orientation of the principal stresses. You don't get the absolute values. To get the absolute values, what you do is that you compare the rotation of the stress field with the stress changes calculated with the source model of the main shock. Okay, I don't go into the detail of that, but this is what this plot is showing on the right. You have the predicted rotation for different value of the differential stress, sigma 3 minus sigma 1. So, in short, when you combine these two information, you can actually derive the absolute stress, which is actually something quite difficult to get. So this is the stress on average, at seismologic depth. Okay, so now let's see what we can learn when we combine this information about the stress field with the variation of slip along the fault. So you might not all be familiar with this kind of diagram. So let me explain what we have here. This is the shear stress. This is the normal stress calculated. What did I say? This is the shear stress. I'm really tired. So this is the shear stress. This is the normal stress calculated on fault with different orientation. And here you have the three more circles. And so this one is connecting sigma 1 and sigma 3, this one sigma 2 and sigma 3, and so on. And the rupture at the surface is nearly purely vertical. From the work of Saif-Sati, we have the slip vector in 3D, and we have the orientation of the fault at the surface, so we get actually the orientation of the fault in 3D, in fact. And so that's how you can calculate actually where the plot in this diagram. For each point along the fault, you know the orientation of the fault. So you see that they follow more or less the largest Mohr circle. So what is interesting is that you see that here you have less slip when you are here than when you are here. Okay? And so the maximum slip actually is more or less at the location where you are the closest to failure. So now let's take a very simple model where you assume that the fault drops from a static friction to a dynamic friction. So mu s would be the static friction, and mu r would be mu d would be the dynamic friction, the residual friction after the slip has occurred on the fault. So you would drop from a point that is on this outer circle to a point that should line on this blue curve. Okay? And actually the stress drop is proportional to slip. Okay? So you can tell that this is where you should have the maximum slip. And here, because those points are much closer to the residual friction, you should have much lower slip. And at this point, the slip should go to 0. Okay? So you can run an inversion and determine what is the best fitting value of the static friction and the dynamic friction that would predict the amount of slip that we see as a function of the orientation of the fault. Okay, so this is a simple equation. It looks complicated, but it's not. This is the expected slip as a function of the orientation of the fault. Here, this is the orientation of the fault, and the change, and the entire thing is actually the stress drop. Okay, so slip is simply the width of the rupture multiplied by the stress drop divided by the shear modulus, and there's a geometric coefficient of order of 1 here. So then you can run inversion and see how the model fits the slip. And actually it fits amazingly well. The blue dots are the observations, and the red dots are the prediction from that very simple static model. I should say that. That's a static analysis. There is no dynamic here. Okay? So from that, you get that the friction, the static friction coefficient is of the order of 0.6. The dynamic friction is of the order of 0.3. Okay. This is the information we need to develop dynamic model of the rupture. And so the next game is to actually take into account the fault geometry in 3D. So here you have the main rupture, and here this is the foreshock in 3D. And then you use the friction coefficient that is derived from the analysis I've just described. And here in that case, we don't use static to dynamic friction. We use a more elaborate friction law, rate on state friction. The reason is that rate on state friction will allow to have friction dropping during slip, so there will be weakening, and it allows for healing. So you can actually use that formalism to produce a model of repeating earthquake on the same fault, because the fault needs to heal. It's the simplest model you can propose to get both weakening during slip and healing after earthquakes. So the game that we played was, we know the stress field from the inversion of the focal mechanism. And so we impose that on the fault, and we play with the parameters that we could not get from the static analysis, so that we produce an earthquake sequence that is similar to the observations. So here's a model that works pretty well. You have a foreshock on that. Let me play the animation. So you have a foreshock on that fault, and later on you have a main shock starting actually on that segment, which is optimally oriented with respect to the stress field. Okay. So and here what is shown on the other animation. Let me I need to start it. So this other animation is showing how the stress is evolving as a function of time during the rupture. So you start on the Mohr circle, and then you drop during the rupture on the dynamic friction. So although the friction law is more elaborate, you have also the equivalent of a static on the dynamic friction that is consistent with what we derive from the variation of slip with the fault orientation. Okay, so now we have a geometry of the fault. We have friction coefficient. We can play the game of running the model over a long period of time to see what kind of dynamic cycle we would get. So the truth is that it's a bit difficult to do with a fault that has a complicated geometry. And so we are not quite there to do that kind of simulation for very long-term tectonics with realistic fault geometry. So, but we are making progress. Now, what do we learn from off-fault deformation? So, as I said, we can compare the field measurements with the displacement from the satellite images, and you get the information that, for example, for the foreshock, 40% of the deformation was actually accommodated on the main fault, and 58% was accommodated by distributed deformation. And that is a sink of energy. Okay? The deformation that is occurring off the main fault should absorb energy. And so you would expect some effect of this off-fault deformation on the rupture dynamics, something that Arshabat and Marion have been studying, actually using models. So what we see that is interesting is that if you compile measurements of this sort for earthquakes that happen all over the planet over the last decade, so for which we can actually document a fault deformation using the same approach I described, what you see is that the off-fault deformation actually correlates quite well with the cumulative displacement. The least, the cumulative displacement, the higher is the fraction of total displacement that is distributed. Okay? You see also a correlation with aftershocks. The more off-fault deformation you have, the more aftershocks you have. Finally, you see also a nice correlation between off-fault deformation and the rupture velocity. The higher the off-fault deformation, the lower the rupture velocity. The most natural way to explain that is that it is related to the fault geometry, that as a fault has more and more displacement, then it becomes less segmented, and you would have less off-fault deformation. And indeed, if you look at the roughness of fault as a function of cumulative displacement, so using the same examples, you see that the faults with more cumulative displacement are more linear, and so that would be a natural explanation. Here I'm showing a result from work by Sarah Visage, Nadaya was involved in that, and Jan Klinger, and which is a nice illustration of this notion that as you have cumulative slip, the fault geometry is actually becoming simpler and simpler, and so you have less. And in this analog experiment that they've done, they see clearly that the off-fault deformation is diminishing with displacement. So this is the same thing that we see in what I've shown. So as we've seen, we can actually predict characteristics of earthquakes based on fault geometry, based on cumulative displacement. And so the question that maybe is really the key thing we would like to be able to answer is how far are we from predicting actually more than that, predicting actually the time and the magnitude of earthquakes. How far are we from using the kind of dynamic modeling I've shown to do that? And to illustrate the difficulty, I'm going to show here a study done by Belle Philippesian, who was a student at Caltech working with Kerisi and myself. And what she did is that she used the coral record of ground displacement. We've heard about that from Natalie earlier today. The advantage of this coral record in Sumatra is that you can actually document earthquakes over a very long period of time. So you can build a long time series. So here you have the earthquake rupture, the Bengkulu earthquake rupture from 2007, the work of Osgun Gonka, so this one is well constrained from inversion of INSAR, GPS, and seismic records. And when you go back in time, here you look at the slip model derived from paleo-earthquakes documented using those coral data. And what you see here is that although the resolution is not as good, those earthquakes are very different. That same segment that is fully locked in the interseismic period is producing very different ruptures when you go back in time here. Okay, so you don't have the repetition of a single of the same earthquake. So we would like our dynamic models to explain this kind of pattern so that we get a full range of possible rupture on their return period and so on. Well, I show this animation. So this animation is the inversion of the coral record over 2 centuries. And what is plotted is the deficit of moment on the fault. So as it goes up, you have more and more elastic strain building on the fault, and then it is released by an earthquake. And here is another one. So what you see here is that not only the patterns are different, but also their timing is clustered. They are not regularly spaced. So we would like to explain the timing and on the extent of the rupture in each of those earthquakes. So let's see how far we can go in predicting ruptures not with real data, but with synthetic data. And here, this is a model that was developed by Ojat Kave, who is a current postdoc in my group, which was tuned to fit the slow slip event that Jean-Mathieu was talking about a minute ago. So these are the slow slip events in Cascadia that were meant to be reproduced by this model. So it's an elongated fault. And let me show you the animation. You do see exactly the kind of pattern I was showing for Sumatra. You can see different segments recurring at different times. You can see coalescence of slow slip events, like Jean-Mathieu was describing. Here it was a good one. There will be another more spectacular one a little later. So here you have a dynamic model that is very similar to it shows the kind of chaotic behavior we see for slow slip events in Cascadia, but also for larger earthquakes, let's say, in Sumatra. So it is simplified. And so the game is, I mean, can we predict earthquake in such a system? So here is a slide just to show the ruptures predicted by the model. And here, this is for comparison, the kind of rupture that were detected by Sylvain Michel during his PhD. And so you can see that qualitatively it behaves very similarly. Okay, now this is the moment deficit on that fault from the model. You can tell that it's quite chaotic and a bit complicated. So actually, you can predict these earthquakes quite well with this in that case. And what is used in the prediction, I won't go into all the details of that because that would be too long. But what is used for the prediction is only the information we know at present. We assume that we know only the slip rate on the fault from the inversion of GPS at time t. And then we calculate the probability of a rupture in the 6 months coming. Okay? So the red dots are showing where the model is predicting an earthquake, and the blue dots are showing, the blue lines are showing the actual realization of the model. So it is doable. The trick is that we analyze the interseismic velocity in the model. We do a PCA, a principal component analysis of the stress field to document the possible stress. So in principle, the stress could be anything. It could be very heterogeneous. But in fact, because of the self-organization from one rupture to the other, the space of possible stress is actually limited. And then you can explore in this space of possible stress, what are the spots that are going to lead to ruptures at different places. So that's what you use to do the forecast. You recognize that if you are at this point in the stress field, a rupture is going to happen at this location in this period of time. And that works pretty well. And here is a forecast of particular events. So this is the truth, and this is the prediction from the model. Okay? And so, yeah, it works relatively well. You can predict the extent of the rupture on the time. We are not quite at the point we can do that for real data, but I think it's an interesting academic topic to pursue. So I think I'm going to stop there for today. Thank you for still being with us this time. I guess you must be frozen or asleep, I don't know. And yeah, thank you, Paul, for the guidance, and we are missing you a lot. Yeah, thank you.